Let's solve this problem. Calculate the surface area of the cone given by z equals square root of x squared plus I squared, cut between the planes z equals 0 and z equals r. So as always, I always recommend the first thing is to sketch what you are trying to find, okay? So this surface, z equals square root of x squared plus y squared, might look ugly, but it's actually very simple. The square root of x squared plus y squared is simply equal to rho, the distance to the z-axis, okay? So this cone is simply z equals rho. Between the planes, z equals 0 and z equals r. So what does this mean? So let me draw, instead of doing a three-dimensional drawing like here, let me draw it what you could do maybe if you are working on this problem. So a very useful trick when doing surfaces that are rotationally symmetric around the z-axis is to, instead of drawing x and y, drawing the axis for rho, so the distance to the z-axis. And since everything is rotationally symmetric, you can just do the volume, the surface of revolution, and it's going to be the same. Okay, so this is like saying a cut plane on a certain plane which includes the z-axis. So in this way of writing it, the equation is z equals rho, and we are saying that z goes between 0 and r. So therefore, z equals 0 is here, z equals r is somewhere here, and then the equation z equals rho is simply a straight line like this, with an angle, with a slope of 1, okay? Which means that if you have reached r here, then rho will also reach r because the slope is 1. Okay, so this is a very nice way of representing this surface by doing a cut plane. Of course, if now we do the surface of revolution of this line around the z-axis, we get this cone drawn here. Okay, so I'm asking you to calculate the surface area of the cone. Therefore, the area is the double integral of ds. So now we need to find ds, and we also need to find what are the two parameters that we are going to use so that we can find the limits and so on. Okay, so clearly I think we should use either cylindrical or spherical coordinates to integrate a cone. Both will work, okay, but let's use cylindrical coordinates. So if we use cylindrical coordinates, then our two parameters are going to be z, which changes from 0 to r, and phi, which changes from 0 to 2 pi. Those can be our two parameters, while rho is kept equal to z. Okay? So therefore, if we substitute, so the general equation for cylindrical coordinates is this. So if we now substitute this into here, what we get is z cosine phi, z sine phi, and z, and we are changing z between 0 and r, and we are changing phi between 0 and 2 pi. Now someone could ask me, Paco, could you leave rho as the parameter changing between 0 and r and have z equals rho and substitute here z equals rho? Yes, you can do that, and it will be identical. You will have here rho, rho, and rho. But maths will give you the same result because math doesn't care if you call a symbol z, or if you call it rho, or if you call it with the drawing of a cat, right? So as long as the limits are the same, which they are the same for z and rho, because they are both changing between 0 and r, as long as the limits are the same and the function has the same shape, then it doesn't matter if you use z as the parameter or rho as the parameter. Okay? Anyway, that was a quick note that I wanted to make there. So now this is clearly a function r which depends on the two parameters, z and rho, which are going to be our two parameters u and v for the calculations. Okay, so now we can calculate. Our next step is we need to obtain ds. because the limits of integration are going to be very simple. They are just constants, but we need to find ds. We can either do it with geometrical intuition, which is what I try to do here. Okay. So with geometrical intuition, we fix z at a given value. So we are here. And we increase z by an amount dz. So we change from this height to a certain height here. So this is what dz is showing. But when we change z by an amount dz, z is our parameter. So we are also changing rho by the same amount. Okay, so that's why both z change by an amount dz, but rho also changes by an amount dz. Okay, so we move from here to here. And therefore the distance that we have moved, if we apply Pythagoras' theorem to these right angle triangles, this distance is going to be square root of 2 times dz. Okay? Now, if we increase our angle phi, which is our second parameter, from a fixed angle phi to phi plus d phi, so we have this angle d phi here. This arc length is just the radius times the angle, and the radius is rho, which is z. So we have rho times d phi, or z times d phi would be the same thing. In this case, because rho equals z. Okay, so then ds is just the product of this length times this length. So ds is going to be square root of 2 z dz d phi. Okay, so that's one way of doing it. If you didn't like this method of doing it, you thought it was a bit tricky realizing that moving dz moved you not only up but also outside because rho equals z, and you just want to apply the recipe. Okay, that's fine, let's do it. So ds is the norm of the partial of r with respect to one parameter cross the partial of r with respect to the other parameter. By the way, here I made a mistake. The two parameters are z and phi. They are the two parameters that we have. Sorry for that. So this times dz times d phi, this is the definition of ds, which I give you as a golden box equation. Yeah. So let's calculate it. So let's calculate the partial derivative of r with respect to z. Okay, so we need to do the partial derivative of this with respect to z. So that's going to be vector cosine phi sine phi 1 cross product the partial derivative of r with respect to phi. So we need to do the partial derivative of this vector with respect to phi, assuming that z is constant. So this is minus z sine phi, z cos phi, and 0. Then after we have calculated those vectors, we will have to calculate the cross product, and then we will have to apply the norm. Okay? Always remember, this simple expression involves many steps. Calculating partial derivatives, then calculating the cross product, and finally calculating the norm of the resulting vector. Okay? So it is deceptively simple, but it always has many steps. So now we did the first step, which is calculating the partial derivatives. And don't forget to add dz d phi. Then the next step is to calculate the cross product. So x hat, y hat, z hat, cosine phi sine phi 1 minus z sine phi minus z, plus z cosine phi and 0. Dz d phi. So we need to find this vector here, which is going to be x hat times minus z cosine phi plus y hat times plus z sine phi. So I already took into account that I had to consider a minus sign, but then I also had to do this times this minus this times this. So that was plus. Okay, so I forgot a minus sign here. Be very careful with the signs, please, always. Plus z hat times this determinant, so cosine times z cosine minus sine times minus z sine. So cosine squared plus sine squared will be simplified to 1. So I will get z. So z times z. So to this we calculate the norm, and then we do dz d phi. Okay. And now finally, so we have done the cross product. Now we have to calculate the norm of this vector. So to calculate the norm of the vector, we need to do the square root of the components squared. And now the negative signs actually didn't matter because we are doing the squares. Okay, so then this is equal to, so once again we have that cosine squared plus sine squared will simplify to 1, so we will get z squared plus z squared, so we get 2z squared dz d phi. So of course z squared we can take it outside, so we get square root of 2z dz d phi. And of course it agrees with what we had from geometrical intuition. Okay, so it's up to you. Do you prefer to struggle a little bit with geometry? It's a bit risky if you get it wrong because it's difficult to check, but I think it's faster. Or do you prefer to take the long path, but at least you can check each step and you are sure that the result is going to be correct? I guess it depends on experience. So if you get very used to it, eventually you will trust yourself to do it like this. But as beginners in calculations of surface integrals, I think this path sounds better, probably. Okay? So now, having found ds, so this was a little detour. So having found ds, we are now ready to calculate the area of the surface of this cone. Okay, so the area of the cone is the double integral of ds, which is equal to the double integral of square root of 2z dz d phi. And we know what the limits are. So the limit in z is between 0 and r, and the limit in phi is between 0 and 2 pi. Okay, so by separation of integrals, because this is a function of z times a function of phi, where the function of phi is simply 1. So this is the integral from 0 to 2 pi of d phi times the integral from 0 to r of z dz times the square root of 2, which we can keep outside as a constant. So this is equal to 2 pi times r squared over 2 times the square root of 2. And this is simply equal to square root of 2 pi r squared, which is the area that we were looking for. Okay? So with that we complete the problem of calculating the surface of this cone. See you in the next video.